the top of the hour. So here we go with session 5 of day 2 of the 2025 RNG Technical Symposium. In this session, we're going to hear from Guild Associates to hear about their offering in the biogas space. You can ask questions on the fly in the chat or the Q&A box, and we'll talk about questions at the end of the presentation as well. So with that, I want to introduce Mike Kanapke with Guild. Mr. Kanapke has over 20 years experience in surface interactions, and over 10 years experience in the RNG business, and over 10 patents in catalytic and adsorptive materials. So Mike's topic is going to be about dry media approaches to gas conditioning and scrubbing. So Mike, with that, the floor is yours.
Thank you very much, Paul. Welcome, everybody. Let me share my screen and my presentation. We're going to talk about dry media absorption, particularly for H2S removal and biogas. It's been reported out in 2024 that over $500 million worth of capital went into H2S removal in the RNG business last year. So it's definitely a potential high marker for operations. And so selecting the correct material for your application and for your site is always preferred to therefore decrease those costs for your operations. So moving on. Sorry. So H2S removal, what we're going to be talking about today. First, we're going to define what is H2S. Why is it a problem? We're going to talk about then H2S and biogas. You know, what areas do we see H2S in? We'll talk about the main ones, what concentrations, potential technologies for removal. These are going to be broken down into non-regenerable dry media, as well as more complicated systems, chemical treatment, and biological scrubbers. We're then going to talk about what's factors for, choosing the right technology for your applications, and then potentially selection of an H2S removal for your site. So, should be a good one. So what is H2S? H2S is generated in biogas. It is extremely toxic. TWA exposures for humans on an 8-hour basis is typically right around 10 to 50 ppms. It's also very corrosive. H2S in water in condensated conditions will lead to sulfuric acid. Sulfuric acid will definitely influence the material of constructions for your site. H2S is also very flammable, and it also has strict regulations for pipeline injections. Those are typically 4 ppm. H2S is also regulated if you're doing biogas power generation on site as well. And these are determined by your Caterpillar engines or engines of similar, and typically range from anywhere from 100 to 200 ppm inlet. So potentially a need for an H2S solution for that. There's also environmental effects. Byproducts, if not treated with a solid absorbent material or knocked out to elemental form, you have the conversion of H2S to SOx, SO2, SO3 in the thermal oxidizer during air permeation. So concerns there, you may not even need to treat it, but environmentally, you may need to have to remove it from your site, depending on state and local regulations. And as stated before, it's definitely an economic driver in this business. Depending on how much H2S is being generated on your site, you will have to scrub appropriately. You don't want to scrub more than you need to, but you want to make sure that you are making your product. All right, so where are we able to find H2S at? And the majority of those are found in 2 main areas. These are anaerobic digestion and landfills. Anaerobic digestion, you're talking about wastewater treatment plants, animal manure collection ponds, and animal plant byproducts waste as well. In the anaerobic digestion space, the air intrusion is typically very low. So therefore you have very low limits of nitrogen and oxygen, and your H2S is actually quite high. It typically averages right around 2,000 ppms on a statistic basis, but can range from anywhere below 500 to 10,000. Typically, sometimes in the anaerobic digest state, they inject ferric chloride or ferric powder, which will limit the amount of H2S being formed in the digester itself, to therefore have to be removed by another solution before going to an RNG upgrader. Landfill is a little bit more different. The H2S concentrations are typically lower than that of the anaerobic digestion sites. However, you have a lot of other potential contaminants for the H2S absorbent material to work with. These are typically VOCs, siloxanes, and can vary on site for different times and different regions, and also different as you process materials and such, and as new materials come in, your contaminants may go up and down, including your H2S. So H2S, what systems require H2S upfront for pretreatment, for their RNG upgrading? Again, we're typically looking here for methane purification. Methane purification would mean removing the bulk CO2 out of the stream. And this can be done through multiple different technologies: water wash, amine wash, membrane, and PSA. I will state for PSA applications, not always. There are some absorbents out there and systems out there that will absorb H2S and then therefore flare it if that is an option. Again, some of these other systems may require a precursor for bulk H2S removal, but typically there is an H2S dry media solution downstream of that, just to have something as a polishing bed, or for a material to work in case the bulk removal system is offline. As this document shows here, there's a lot of media out there. There's a lot of solutions out there that require H2S removal upstream. Again, removal H2S up front will decrease the cost of material construction, because now you do not need to be stainless steel. You can be carbon steel or coated carbon steel, because you have no risk of sulfuric acid interactions with your material reference. As you can see for membranes, the amount of pretreatment that is required, VOCs, etc., also limit the effectiveness of the membranes. The last thing you want to do is have H2S carryover into these subsystems. So again, I've broken down the H2S technology options into what I call dumb systems, and also to basically chemical or biological scrubbers. What is a dumb system? Well, a dumb system is just a vessel that gets filled up with material, and the inlet of the material, you have an H2S laden gas, and the outlet of the material, you have a gas that is purified of H2S. These are where dry media, non-regenerable dry media, take place. Now, the term non-regenerable dry media means that it has a service life. The material is going to get replaced out in frequency once it is exhausted. There are materials in there that regenerate in situ, but it will eventually have an exhaustion rate and a service life for the treatment. You start talking about higher loadings where H2S values are increasingly high in the inlet, and then you start looking at chelate systems and iron caustic scrubbers, and then also biological scrubbers as well, in which you are expected to have right around thousands of pounds of H2S inlet per day. These require a technology that makes sense for the application. So to go on to the non-regenerable dry media first, we're going to first talk about activated carbon. So carbon's been an absorbent for a very long time, and it's naturally suited as well in the biogas spaces, for removal of compounds, for H2S, for VOCs, and for a multitude of other applications as well. Now, I will state, for this presentation, I did not call out specific carbon manufacturers and carbon products. I just basically talked about groups or subgroups of the technology, and then a selection can happen within the subgroup. Carbon is unique because it will have both physical absorption through the micropores of the interactions with the carbon material, as well as chemical absorption with impregnants on the carbon to enhance its performance and enhance its life in the operation. Now, these impregnants can potentially walk depending on the amount of water, or they can get blinded by other materials as well and other compounds. But for the most part, they are very effective as a working group on the carbon material. Typical impregnants on carbon is typically iron, zinc, copper, and then you also have the alkaline wash, where you expose the carbon to a sodium hydroxide solution or a potassium iodine solution as well, making the carbon alkaline, therefore able to treat sulfuric acid gas, acid gas in H2S. Next, we're going to talk about iron hydroxide. Again, this can be an impregnant on a carbon material. It's offered in multiple of applications. One as a granular form, as well as a coating as well. The reaction is very simple. You have iron reacts with H2S, you form iron sulfates. If you have oxygen present in the stream, you potentially have a regeneration reaction if sufficient, where the iron sulfate will then react with the oxygen and water to form your iron oxide material back and elemental sulfur. Elemental sulfur will accumulate into the pores until the material is no longer able to be active. It operates in this absorption, chemoabsorption, oxidation for H2S removal. Okay. The next one is one that's been in the industry for the longest amount of time, is the iron sponge. It's basically another iron impregnated material, typically on a very cheap source of substrate, typically wood chips or aluminum basis. And it's an iron impregnated material, therefore giving you a similar reaction for H2S removal. You have the chemoabsorption reaction and the regeneration, again, when present in oxygen. And the last technology, and the one I'm most familiar with myself, is the BSR50, which is a mixed metal hydroxide reaction. Again, here it's not only an iron source material, it is a mixed oxide material with other metals in there to formulate a composition to yield, one, that's reactive, and two, also having a high capacity and high pore space for a mesoporous substrate. This results in a high end capacity for the material and good utilization, assuming that you have the prereqs of oxygen and water. So, talking to our end users, we put together a slide of stating how it works in the operations and what are the good and bad points of each operation or of each technology in the RNG application. With activated carbon, again, CapEx is typically very low. These are, not complicated vessels. Typically, they're at low pressures. We're talking anywhere from negative on the vacuum stage, or on a positive pressure up to 5 psig, which is typical. The material costs, media costs are typically low. They're on the orders of $1 to $5 a pound. And the operational costs, again, you don't need a skilled operator to run a dragger to understand the input and output or the effectiveness of your material. So overall, it takes a very low operational cost to run the system, maintain the system, and have a valid product to therefore not break down for the operations. Hence the reason why dry media is typically the path to go if you're able to operate within those parameters. Highlighting some of the points on the board, the issues with activated carbon is that you have competing absorption with other volatile organic compounds if present in the stream. You always will have a disposal for all 4 technologies. Typically, those will go through RCRA testing to validate that they pass TCLP and therefore be able to be disposed into a regular landfill. Your affinity to other those metals, typically arsenic, will also be a potential selector for your technology. Iron hydroxide, you get a little bit more bridging, which causes a change out to be a little bit harder than other technologies. Basically what happens is, since it has a very low pore structure, you have bridging of sulfur on the external surface. Sulfur next to other sulfurs will bridge and form a hard material and make the changeouts a little bit more harder. And with iron sponge, this is the one that is noticed for the most difficult change out for the material. So things to consider, as for a capacity basis, the mixed metal hydroxide has the highest capacity, followed by the activated carbon and the iron hydroxide. And the iron sponge, since it's just a very cheap material with a low cost, it has the lowest capacity out of the bunch. Again, I was going to touch on the other chemical treatments. These treatments potentially will have a polishing bed downstream, which would then be a dry media solution, because the operation of such is typically requires a skilled laborer to run and operate these systems. This is a iron chelate caustic scrubber. It's a very similar reaction. Depends on just the absorption mechanism for H2S. You have inlet sour gas coming into your reactor. You have an exchanger, and your caustic or your chelate will be used over time, which then causes another pump to actively measure and pump into the system itself. You will make a spent waste. It's a sulfur cake, and will need to be removed periodically depending on your usage rate of your system. Process equipment needs to be maintained to be viable. So, uptime is definitely a factor. And for, systems that have very large inlet H2S concentrations, you would be looking at a biological scrubber. This would be to remove the H2S material or H2S compound through microorganisms, basically SOBs, sulfur oxidizing bacteria, converting the sulfur to elemental sulfur. Again, you're going to have the appropriate operations maintain the operation to be effective, and potential downtime and potential uptime of the plant is dependent on the operations of this system. Similarly, we polled the user community for the operations of these systems, and the feedback was as expected for replacement and maintaining of that. Again, startup, disposal, maintenance, and temperature were a lot more sophisticated than that of what we call a dumb system, which is just the dry media replacement. But again, utilized for the gas and for the application. All right. So, how do you determine, what technology to choose for your application? What makes sense? And so the first thing that I would always recommend is that you calculate how much H2S you're inputting per day. And that can be achieved by utilizing this equation here, which is the fourth point down. And then also understand your operating parameters of your site. If you're a northern site, will you experience colder weather, colder temperatures, in the winter? Or if you're a southern site and you experience hotter temperatures in the spring, summer regions in that regard. This will all, dry media solutions all have temperature ranges of optimal operation. And being able to operate the majority of your time in those operating range will yield out a good solution for you in that regard. Understand pressure effects. Typically, as stated, the majority of all applications are low pressure. There are high pressure applications as well. At high pressure applications, potentially, you have an interaction with CO2 to form carbonic acid, and then therefore that has an interaction on your reactive material. And then also your water content. Are you have saturated gas? Are you dry gas? I've been around for a while, and it's surprising sometimes you presume this one would be the majority of saturated gas would be the consistent, but dry gas applications and chilling applications are becoming more frequent, we'll state, and understanding, your technology or the technology can work in those conditions as well. And then lastly, what are your exit requirements? Are you trying to meet 4 ppm, or are you generating to a biogas Caterpillar engine or power generation in which you're able to, have a stream with a higher H2S content to it. H2S, abatement is an abatement technology. The less you have to do, the more economics that you are favored for your favor. So, do what makes sense. So with this information and with the amount of pounds of H2S you have per day, this chart was constructed on an economical basis to yield out what technology may be suitable for your application. Now, again, all applications are independent depending on other conditions, pressure, temperature, oxygen, water content, which will move a potential technology further or less depending on your operating conditions. But as you can see, the lower H2S values per day, would yield to a, non-regenerable dry media solution. And as you increase those, you get to a biological scrubber. For the material that I promote, BSR 50, if I use an example of, if I have a capacity of, I absorb 1 pound of H2S per day, and I would require for my material 1 pound of BSR 50 for this application. When you start wanting now, appropriate change out is typically, half a year. So it's basically 180 days. So I would typically want to have, my input is 100, then I would want to have 180,000 pounds of material. At these points, the economics doesn't really favor a dry media solution. You want something to have, be able, because that's a lot of material to change out over time. So having smaller systems and such, or, being okay with the appropriate change out interval, is key for your application. And then finally, what is your last variables and such for, CapEx? Are you a new installer or you have existing vessels? Obviously, if you're able to work with your vessels, you potentially are, don't have to have the input of a new cost structure for that, as well as, how many changeouts a year, difficulty of changeouts, the amount of H2S inputted into it, the overall cost to remove H2S is on a yearly basis. This includes the cost of the material, the cost of the equipment to run the material, and the cost of changeouts for a totality of that. So understand those, understand your site. Are you reliable for flow? Do you have consistent flow? Are you on off? Are you, are you reliable for your oxygen? Do you have a leaky digester where you potentially need to input oxygen to make a solution work? And then also, do you generate a waste? You have wastewater treatment options to catch condensate that comes off your material or is a byproduct of that and potentially has other contaminants into it that would need to be properly disposed of. So again, appreciate the time today. Wanted to give you some general information on H2S removal and H2S removal technologies, and hopefully, provide some input on how things are effective in the application and, solutions for the industry.
Great. Thanks, Mike. Good overview. A couple questions came in pertaining to materials of construction. So on things like the absorber vessels or the interconnecting piping, can you comment on stainless steel versus other types of materials for the vessels and the piping?
Yeah, typically, if you're able to do, if you have low pressure, the best is always FRP. Okay, but that only rates up to 14 psi. Depends on your site in that regard. Typically, what's used in the industry is a coated carbon steel material. And that is used in the interpiping as well. Other people do stainless steel in that application, but again, depending on how much H2S you have coming in and the amount of deterioration effects potential, will limit will potentially yield a resulting factor for you.
Okay. So I'm going back to the example you gave where you came up with 180,000 pound vessel. Just walk through how you would size vessels again, as far as, do you say to yourself how frequently you want to change out? Do you say 2 or 3 times per year, and then you kind of use your daily consumption? How would a guy like you go about sizing vessels?
Me personally, 3 months is definitely the most I would always recommend for a new installation. All right. If you're changing out a vessel every month, the risk for potential downtime is significant, right? Where if I have to, I'm not able to, most vessels are in a lead lag configuration. I'll state that, right? So that way you can always operate while doing the change out. I forgot to mention that during the presentation, but that's a very common tool for this application and this use. So if you're changing out things on a monthly basis and such, that's a lot of quick, and it just doesn't yield to a very smooth operation. You're asking the operators to continually monitor. So, the benefit here is you want to make sure the material is being utilized, and then you also want to risk the investment or decrease the risk of investment for the operation as well. So, me personally, doing changeouts on 3 times a year is beneficial. You actually make sure you utilize the materials. You don't want to have a change out of every 5 years. The potential loss of risk of such, on a new installation is too high. If there's an act of God, a lightning strike, a flooding event, potentially you lose that investment over the course of the material. So if you're able to plan it out, change out twice a year, 3 times a year would be preferred, and something that I would recommend for any application for a dry media solution. Now, that being said, as stated earlier, you have potential, bioscrubbers with downstream operations behind that. Those are typically, sized for 7 days of operation, just because the input is so high.
Yeah.
Right.
Got
Smaller
it.
vessels also lead to smaller capital expense as well, right? So, but you're also predicting for the future what the H2S concentration is going to be in your source gas. There's been a noticeable trend of H2S increasing due to the amount of gypsum board being deposited into new landfills due to act of God events, causing housing destructions and such.
So one thing that comes up that people like to talk about with dry media is the ease of replacing the media. Some media is easier than others to get out of the vessel once it's spent. Can you comment on that material you're promoting and how well it does coming and going out of a vessel?
Yeah, I mean, we'll state the operation is key for the disposal of any material in that regard. And typically what needs to be mitigated is a knockout drum in front of a vessel to mitigate any any excess water and liquid water going through the bed. Liquid water going through a dry media bed is always problematic. One, it potentially causes channeling if you're top down, and two, you potentially are blighting your material and such, because you're having to absorb H2S through water to your material. Ease of material on the way out. Obviously, everyone's heard the horror stories of iron sponge, jackhammers, etc., getting it out, tarps in that regard. For carbon material and for the material that I promote, typically we remove the material out of the bottom manhole, and after getting through the crust layer, it's able to free flow out. So it doesn't agglomerate on such, because you don't have the external sulfur on the outside.
Yeah.
Okay.
Yeah,
External.
important stuff.
Yeah.
Good. So, Guild, certainly one of the established granddaddies in this space when it comes to dry media absorption. So thank you for your wisdom. And there was only one other question that came up on use of PVC or PVC piping on vessel skids, PVC or CPVC work.
I've never seen one with CPVC. I'm sorry.
Yeah.
It's always steel. I presume at some pressures it's viable. But be honest, I've never seen one in industry that has been PVC. I guess it could be work. If you're going to go down that route, you definitely use CPVC just because of temperature effects. It gives you a better range, but I personally haven't seen it in that regard.
And so the
Have you
range of
seen it, Paul?
operation. No.
No. Yeah, for any sort of pressure event, I definitely would not be gluing, any sort of piping in that regard. I would
Yeah.
definitely use a coated steel or stainless steel.
Okay, well, good. Well, thanks, Mike, and all the guests. Feel free to reach out to Mike if Guild can be of service to you on a dry media application. Mike, we'll let you run, and to the guests, we've got half-hour break here to IVAS coming up. IVAS, formerly known as ZBEC, they're offering our PSA gas upgraders, and they're going to talk about gas upgrading and CO2 recovery from RNG projects. So we'll see you in 28 minutes.